Well, I'm down to my last bipod adapter for an M99. Here's the finished product right here. It adapts a Barrett M99 rifle to a standard Picatinny rifle. And I was going to take a picture of the progress, but I thought, what the heck, let's just take a video and I'll show everyone how it's made here. So let me go over here to I'm on my 3-axis. Let me go ahead and hit the start button. And we'll be able to watch this process go from start to finish. I'm filming through the window right here, so I just cleaned it off. I'm not sure how well it's going to last. I just turned the pressure down on the coolant down to 150 from 600, so hopefully it's not going to spray all over the place. I'm using a 2-flute half-inch end mill right now, running it pretty slow. Carbide's expensive, and I just I'm only making about 50 of these, so if I was going to tool up and make 1,000 of them, I'd really push these and optimize the tools. But for this, just using a regular 2-flute half-inch carbide, running at about 45 inches, 50 inches a minute right now. This is just a roughing pass. I'm making actually 3. We've got Op 1 and Op 2 in the vices. On the left side is the first operation. On the second side there is the second operation. That coolant there is water-soluble oil. It just comes in a bucket and you mix water in with it, and it makes a lubricant that allows the tool to slide through material easier, as well as cut it down, and most importantly to clear the chips out of the way, because you don't want to be recutting chips. You already cut them. There's no point in cutting them again. We're just about to surface this material flat. We're going to be making 3. You hear the RPM speed up here. This is where this end mill really shines. You can see the massive amounts of chips coming off of it. I'm running it at, 8,000 RPM, which is the spindle limit of this machine. But doing right here about a half-inch width of cut, and a full width 1.5 inch depth of cut. This machine path right here isn't something I programmed. This is something that comes out of HSM Works, which is a SolidWorks plugin that allows, once you model it, it allows you to, it's called adaptive clearing, and it allows you to make all these weird little tool paths and really optimize the way that the cutter goes in the material and comes out of the cutter, so you can really get aggressive and run really high removal rates. So you can just let it go, and you can watch the chips fly off of this. But it's a pretty healthy evacuation of chips. I did turn it down just a little bit because I turned the coolant down, because normally if I run this thing at 600 psi, which is where I normally run it, it would just be a fog of the coolant. So I don't think we're going to have any problems here. I've run it this low before, and really, so long as the chips get out of there, we're all good. There's more than enough coolant here to keep the part cool, but then also keep all of the tools lubricated. So I've got about 10 tool changes that this machine's going to go through to finish this part. It is a Picatinny rail adapter, so it does have some intricacies to it. But something easy I can just punch out on the 3-axis, and I don't need to get on the 5-axis to do it, which would just take forever, because here I can do Operation 1 and Operation 2 and have a finished part come right off the machine 3 at a time. I mean, the cycle times are a little bit long. The tool paths aren't totally optimized, but like I said, I'm only doing a run of 50, so it's okay. I think my cycle time here is a half hour, so if I get a half hour and 3 finished parts come off, that's 10 minutes per part. That's acceptable for these small batches. And I'm doing small batches because you could get them anodized, around the corner here at a local anodizer, type 2 or type 3. I choose the harder anodizing just so the finish stays longer. This is actually a really important step right here, which it's going to fail because there's a chip. I have this thing hot wired so I can open up the door. So I got a tool break detector, but There was a chip on the tool brake detector. I didn't blow it off because I just modified it, but I'm just going to go ahead and override it here in the controller. It did detect that there was a tool breakage. Like I said, I've got this thing hot wired, so it always is sensing an open door, even when there's always sensing a closed door, even when it's open, just because I want to be able to reach in there and do little stuff like this every once in a while. So here we are. We just have a 1/4-inch drill coming in. The only reason to do this is to get material removed out of a pocket that I'm about to machine. This is just a little bit of experience goes a long way in doing this, because when you're milling these pockets, you got to get the chips out, and you also got to make sure that the coolant stays inside the pocket. So I'm about to ramp in there with a 3/8" end mill, and just pre-drilling it gives it just a little bit of space for the chips to go, so they don't bind up and end up breaking a tool. These end mills, they're expensive, and I am running solid carbide end mills for all of the tools. They last a long time, but boy, if you do something stupid in the programming, or you're not watching what you're doing and you end up breaking one of them, it's painful. It hurts. It hurts the pocketbook. It hurts the ego. It hurts everything. And I hate going into my spares just because I did something stupid like let chips pile up and not get it out. What I'm doing now is pre-drilling the inner diameter of a 1/4-20 thread. Drills are amazing. The amount of material removal you can get is just phenomenal. The machine's going up and down right now. It's called a PEC cycle, and what that does is allows the chip to break and then also come up through the hole really easy and not bird's nest around the tool. Last thing you want is have all of those chips wrapped up around the top of the tool, because it doesn't give the evacuated chip anywhere to go, and it also can potentially scratch up the part, unbalance the tool, everything. So you can't just drill straight down. You could if you had some through tool coolant, which actually is very neat. It spits out coolant right through the tip of the drill and allows you to just blast that drill in there as fast as you can imagine. But I don't have that on this machine, so we're just doing the old school PEC cycle, and making sure that the chip breaks and making sure we can get some coolant down in that hole to keep that tool lubricated and good to go. This next check here is absolutely important, because if that drill was to break in that hole, I would need to know it. Because of this next tool that's going to come in, which is just one of my favorite tools, it sure saves you being able to use this next tool and use it appropriately, which is a thread mill. So what we're actually doing this next one, instead of going through and running a tap down into this, which I guarantee you break half the time, it needs a bottom thread. It's just the way we designed it. And what we're actually doing is just going through here and circling. You can see the table moving, and we're actually cutting a thread to the exact 1/4-20 diameter. It's just it's an amazing little tool, and it saves you so much time and gives you the absolutely perfect thread fit. I mean, granted, on this part, having it an extremely tight thread isn't important, but nevertheless, it is really nice to be able to control the thread. I would turn the coolant off and stick the camera in and show you, but this is such a tight little tool that I'm afraid if I did turn it off, I'd weld the chips up, pack it up, and break it off. And like I said before, these tools are expensive, and we do not want to break them at all. But I'll get a close-up of it when it pulls out and does its final hole here. It's doing, as you can see, it's kind of starting to take shape. We got 3 parts starting to form up here. God, one of the things I absolutely love about being able to make parts out of solid metal is just how reliable and how precise, and just how cool it is to be able to come in design something in SolidWorks, have an idea, and then be able to program the machine to come out and cut it out for you. I mean, there is some, you know-how and some learning pains on how to get from SolidWorks to finished product, but boy, it's just so cool to be able to use the mind for creativity. And you just heard the air compressor blow off. That's my California Air Tools compressor. It's I've got 100 gallons of air in the shop here, but that is my quiet tool. Oh, we just finished, so here, let me go ahead and open this. You can see how tiny that little tool is. It's just big enough. Let me see if I can get around here, focus, to cut the thread. And we're just checking that we didn't break that off while we were in there milling those threads, but it's done with the threading. Of course, I'll check it before the part comes off the vise, just to make sure. We're just grabbing another end mill now to go ahead and do some finishing work on this. You know, one thing I do is I really take my time and try and make the absolute best product that I can. I mean, let me show you what I'm talking about here. So here's one that just came off the machine a little bit ago. As you can see, all the lines are sharp and you know, beautifully chamfered. Yeah, there's a chip right there, but you can't really see it. Threads are cut perfectly. You know, it's just ready to go. Basically, it'll go right to the anodizer, and it'll come out looking perfect. I don't have to finish it. And you know, that's what we're doing right now, is we're just running an end mill out at about 1/1000th per tooth. And all that means is we're running at a slower speed just to have a really nice finish. You know, it's only a couple minutes, and the parts come out looking so much nicer than if you just, you know, run it as fast as it can go, maximum, you know, material rate. You got chatter on the tool, and then, you know, then it's up to the anodizer to either tumble it or you know, just blast it like crazy. With this, it just goes right to the anodizer with a little bit of blasting, and it just comes out looking perfect. You know, it does take a little longer, but you know, hey, that's all right. So it's going to go ahead and go around, move really slow. It's moving around those corners really slow, so it doesn't get a chattered finish in the corners. I guess, you know, let me pause this right here. This is just, you know, you can't really see it anyways, but I got another tool coming up that is just neat. I'll pick this up in a second here. All right, here comes the part that I talked about earlier, where I am ramping in, and I'm using that pre-drilled hole to be able to, one, get some coolant down in the pocket before the tool gets down in there, and then also to be able to just have a place for these chips to go as kind of a buffer zone. You know, let me see if I can turn the coolant off for a second, get in there and just show it real quick. Okay, we just started, I'm just going to go quick here. So I just pop the coolant off. You can see how those chips build up the well. As quickly as I can here. There we go. So you see what I mean? If you let those chips build up in there, what'll happen is they'll get compacted into the cutting flutes, and you'll end up breaking one of those end mills off quicker than you can imagine. I've got a box of them over here, just trials and tribulations, and learning how to do all this stuff. You know, actually coming up is another one of the coolest parts about doing CNC machining, and I've got a chamfering tool coming up. It's a 30-degree cutter that will actually just go ahead and break the edge and give you a really good looking finished part. What we're doing right now is just going back into that same pocket. That before was called a roughing operation. A roughing operation is just a way to get material out as quickly as you can. You're not so much finished and, you know, worried about exact precision. You're just worried about running a tool path that'll get the chips out of there as quickly as you can, so you can come in with this now and leave a really nice finish on the bottom end and the sidewall. And that's what I'm doing right now. As you can see, we're just flooding it and making sure that the tool is very happy, running at a very conservative tool removal rate, making sure that we don't have any chatter and that, you know, it sounds good. Let's see, this next tool I can go ahead and open the door. Like I said, I've got this thing hot wired so I can open up the door. We're going to change to this chamfer tool, and this is so cool. I'll be able to get a close-up of this one as soon as we're in there. Let this machine whip around and grab the chamfer tool. I got my finger on the button here to turn the coolant off as soon as this thing starts up, because I do not want to take a shower. So this tool here is spinning up to about 8,000 RPM. And what it's doing is it's just rolling around the edges of all of the surfaces that we just cut, just putting the slightest little chamfer on it. So there are no burrs, there is no hand finishing needed. It's just all perfect. And all it's going to do is follow all the way around the part at exactly the same location. Like, when I say exactly the location, this machine is capable of accuracies within half of a 10,000th, which means that if you sliced a piece of paper into, roughly 10 pieces thickness, that's how accurate this machine is. So much more accurate than a person can really measure. I mean, of course you can with micrometers and whatnot, but it's just here, let me. You can see the code that it's following, and this is something that was all outputted by a SolidWorks plugin to do that. But each one of these lines that move corresponds with a movement right there on the machine. So pretty absolutely fascinating here to see this translate into this, which started off as something in my mind, and ends up being a physical product here. So I can't remember what are we doing next here. Are we moving on to the other operation? I'll be able to tell really quickly on what tool we grab. Oh yeah, we're grabbing the big 1/2" tooth flute. I better shut the door, else we're gonna get wet. You can see the chips kind of stacking up on the vices. That's because I am running at like I said, what I can't remember, 150 psi as opposed to 600. If I had it turned up to 600, we would just be blown out with that white milky stuff, and the chips would not stack up there. They'd be evacuated out to the actually, let me show you this really quick here too. So this is one of the best things about having a CNC machine is here the chips come down, run over here up the chute, and whammo, right into the garbage can. And all you gotta do is empty the garbage can. Don't really ever have to clean the machine out, so that's where the waste goes. And then the water gets recirculated and separated from the chips as it flows back into the recirculation. But of course it goes through a couple filters because you want the coolant as clean as it can be going to the cutting tool. You don't want, like I said earlier, you don't want to be recutting chips, and if you're recirculating chips through the machine, obviously that's going to let your surface finish and your tool life suffer accordingly. So got to have good clean coolant in the system. It's got to be have the correct pH balance. It's got to, that's one other thing. If you don't have the right pH balance on these cutting fluid, it gets to stinking bad. And as you can see, I got a little surface rust building up. That's just because I've been running it slightly lean and not on purpose. I just haven't checked it. I checked it a couple months ago. It was good, but obviously I need to get back on the coolant schedule and make sure that my coolant is pH'd correctly, so it doesn't provide any of this little surface rust. It's no big deal. It just wipes right off. But still, you gotta treat your equipment well, and it'll serve you for a long time. I switched over here to a 1/4" end mill, and you might say, why the heck are you using a 1/4" tool? Because you've got a lot of material to remove there. Well, you can spend a lot of time switching tools a lot, or you can just pick a couple of tools that you're going to use. On this project, I'm using a 1/2" end mill, a 3/8" end mill, and a 1/4" end mill. And I'm actually going to cut these parts apart right now. They are individually secured, but to try and maximize part density, I put the parts in there as tight as I can, and we're about to see that 1/4 inch end mill go in using a roughing strategy, which that's what we're doing right now. It's using adaptive clearing to go in, and I think it's going to hit it on this pass. It's going to hit it on this pass or the next pass? Nope, next one. So I could have used a bigger end mill. There it goes. So what it's doing is it's circulating in and circulating out, loading the cutter and unloading the cutter to be able to separate these parts. And you know, if you just plunge that end mill down and say gave it a command to go straight across and cut them out, what you'll end up doing is welding the chips in there, and you'll end up breaking a tool. So that's something that one of these, yeah, you can see the glass already fogging up. I can see the, this isn't going to last very long. But yeah, I'm using like I said, a 1/4 inch end mill instead of a smaller one, just because I can do this all in one job and don't need to, or one operation, and I don't need to do a tool change. So if I, you know, I could switch and use a 1/2 inch end mill and step it down to a 3/4 inch end mill, but you know, it's not too bad if I just do the whole thing in a 1/4 inch end mill, because you know, you got to factor in a tool changer time into doing this. But you know, not like it's an extremely important. It was just kind of a, hey, I'm programming it and I can do it all in a 1/4 inch, so let's just do it all in a 1/4 inch and be done with it, and you know, not have to program another step in there, because every step, you know, means another, you know, time that it's got to come down and, you know, test the tool to see if you broke something, and just another step for something to go wrong. So I say do as much work with one tool as you can while it's in the tool holder. So let's see, this thing ought to be done about now. You know, I want to let this thing go. I'll catch it back up when it starts to cut the Picatinny rail, which is another pretty cool operation. All right, we're back. We're cutting the Picatinny rails for the bipod adapter right now. I've running a 1/8 inch 3 flute tool right now, and I've got it choked up pretty tight. You know, that's so I cut the pick rails extremely straight and sharp. I know it's not extremely important for a bipod mount. I keep the, you know, I imagine everything is going on an optics rail, or, you know, I just, you know, I always try and do the best work I can do, and, you know, sometimes that means specialty tooling. Here, we're about to stop that, and I can show you how tight I've got that thing choked up. Which, you know, we're obviously doing the tool break to tighten it out, but you can see just how little stick out that has. You want that little stick out because it doesn't let the tool flex in there, so it cuts those rails very straight and very sharp. But you do need to run it just a little bit slower because you don't have that coolant blasting down on there. This is a really neat tool. This is a form tool. You can see it's got a little V channel in there. And let me get out of there before I don't take a shower. What it's going to do is cut the actual rail section of the Picatinny rail. I already have this dialed in, so the tolerances are perfect, but it's just going to blast across the side of it. It's a 4-flute tool, and aluminum 4 flutes aren't an optimal, I don't know, say cutting tool, because they load up a little bit, but you know, the place that made the form tool for me would only do it in a 4-flute, so I kind of have to run this thing slow. Works great in steel, but in aluminum you definitely want those 2 and 3 flute cutters, not the 4, 5, 6 flutes, because of how tight the cutter is. But this works. I'm not going to turn the coolant off with this because I don't want that thing to pack up. But as you can see, it is cutting one side of the rail and cutting other side of the rail at a moderate rate. You can hear it sounds perfect. You just get that perfect, I don't know, machinist hum on a climb mill. So we'll let this finish. I think we're going to be engraving next. You know, it's just my little logo, says SNIPETAC on it. You know, I'm not a really big proponent of having, you know, big marketing and branding stuff all over the stuff. I figured you bought it from me. You didn't buy it to have me advertise on your rifle or on your motorcycle or whatever. So I try and leave the branding, you know, really light and tasteful, but you know, still leave the maker's mark on the product, which of course is me. So you know, that's coming up. It's a tiny little influence. It's actually really interesting to watch. Coming up here next, I can turn the coolant off for this. It's just because it's taking such a shallow, tiny cut. We'll be up in a second here. I think it's coming up next. If it is, it's going to be a tiny little 1 millimeter ball end mill. Yep, that's it. Look how tiny that little cutter is. Let me make sure I catch the coolant turn off here. There we go. So let me get in there tight. And you see it's just ever so lightly going down, just a couple hundred thousandths, and engraving my mark into it. Look at the how complex the code is to do that. Every little that's a good one. That must be an arc or something in the S or something. So it's running down. It'll finish, and I think we've got a couple little miscellaneous deburring tasks. You know, using my favorite deburring tool. You know, trying to do everything that I can while it's on the machine to deburr, finish up, make it absolutely perfect, so I can just hand it right off to the anodizer and not have to do any sort of finishing work. And you know, that way too it holds its tolerances, and it's just as perfect as I can make it. So we're just finishing up the last engraving mark here. Actually, let me hit it with a little bit of coolant just to be on the safe side. I'd hate to say I don't need it, then break a tool, and you guys might catch me saying a bad word. Actually, I've got a bunch of these tools, but I still don't want to break them. You know, because then you got to retouch them off, remeasure them, you know, find the place in the code that you left it. Or what I usually do is if something goes wrong during this step, I just scrap the whole batch and start over again, as opposed to, you know, trying to fix it, because sometimes throwing good work after bad doesn't get you anywhere. So yep, what we're doing here now is grabbing that chamfering tool, and we're just going to break a couple of the edges that we can, or that haven't already been hit. Just running that tool across the edges. I think we're running at 1/1000th and a half per tooth, which leaves a really nice finish. You know, definitely no chatter marks or nothing. So as soon as that's done, and then I think we're going to grab one other tool and try and deburr the back side of it. That form cutter, it throws up a burr right there on the end, right here. You can't really see it because of the coolant. And I think, yeah, we're grabbing that 1/4 inch end mill next. And we are just going to close the door here. Yeah, that's exactly what we're doing. We're just going to break that chip right there that the form tool left. It's kind of funny, some of your machining strategies, you program it, simulate it, run it, and then you look at the part afterwards and you say, okay, where did this thing throw up a burr, and where do I need to run one more profile operation on it? And unfortunately, it's kind of like you can't really see it until you see it. So you do your best to try and visualize it during the initial setup, but I'm always doing the initial programming, then looking at the part, measuring it, and making sure it's all in tolerance. And that should be it. Yep, we're back to the very beginning. So we were able to see this thing. Let me get this over there. It'll blow. Of course, the air compressor just kicks on. But there it is. 3 finished parts. And there's the back side of it. So now what I'll do is I will take this side, flip it over here, put a new piece of raw stock in, and let it run for about a half hour, and we'll have 3 more parts coming right off the assembly line. So I think I'm doing 50 or so. It's a small run, I know, but when you're making parts for a specific product, in this case a Barrett M99, I don't want to make 1,000 or make 500 and then have them change the design or something, that I'm stuck with all this stuff that is only good for somebody that's got the old generation firearm or whatever. So I kind of keep the production real low, and it's fun. It's something I do on the weekends, and hopefully this is going to be the retirement gig one of these days if I can get out of the day job. But there it is, hot off the CNC, a bipod adapter for a Barrett M99. Thanks.